it's good practice, as anyone who's taught knows, to start with the thing that you want the audience to take away. So I'm going to give away the ending of my 3 years of Gresham lectures. The universe, we're pretty sure, is really big. And if you remember nothing else from these lectures, I want you to know that it's really, really, really big. And that's the topic of this evening. It's much bigger than anyone would have thought when this series of lectures started in the late 16th century. We've come to realize that far from being an important part of the universe, we live on an ordinary star in an ordinary galaxy. And though it's beautiful to look at in the night sky, when you look up, you should realize that you're looking at a tiny selection of a few 100 billion stars that make up the Milky Way galaxy, and that galaxy, which we once thought was all there was, is one of hundreds of billions in the entire observable universe. And in fact, there's good reason to believe that the observable universe is a tiny fraction of the whole. If that wasn't enough, you could sort of add this up. It's often said that there are more stars just in the observable universe than there are grains of sand on Earth. And as I know a Gresham audience likes accuracy, I should say we're not sure whether that's true or not, but not because we don't know the number of stars, it's because we don't know the number of grains of sand on Earth. So if there are geologists in the room, we can talk about that later. I feel there's some slacking going on. But this is a really strange position to find ourselves in. We stand, we marvel at the cosmos, we enjoy looking at the night sky and the wonderful pictures that we get from telescopes, but it's hard not to feel lost in this vastness of the universe. I'm a great fan of the 1930s philosopher and slightly strange sci-fi writer Olaf Stapledon, who wrote about feeling something awesome but terrible in looking at the night sky. And so one of the things we have to deal with at the start of thinking about astronomy is how to reconcile those two feelings. And one way we do it, I think, is to talk about the fact that out there, amongst this vast universe and all these stars, there might be places that would feel familiar to us. I don't know, it's the celestial equivalent of when you're abroad and you've been away for a while, you start craving a cup of tea and a piece of toast or something like that. And so when we talk about, for example, discovering planets around other stars, a growth industry in astronomy, which we'll talk more about next time, we start to do things like compile lists of the 10 most Earth-like places. We go out into the universe to look for home. And ignore the fact that there are also things like lava worlds, places unlike anything in our solar system, small, formerly rocky bodies so close to their star that they must have a molten surface. I'm reminded of Richard Feynman, the strange and complicated person, but as good with words as he was with equations, who, thinking about this stuff, said, "What men are poets if they can speak of Jupiter if he were like a man? But if he's an immense spinning sphere of methane and ammonia, must be silent." And I am no poet, but we'll try and think about the grandeur of this instead of just sticking to the familiar. So the way that I deal with the billions and billions and billions that add up in this subject isn't, I should say, by having some deep understanding that comes out of being even Gresham Professor of Astronomy. When I ask people, when I tell people I'm an astronomer, I usually get one of about 3 reactions. The first reaction is, have you found aliens? I think we're covering that in lecture 5 of this year's talks, so I will leave you in suspense for now. This is no. The second question is, do you know Brian Cox, at least in this country? The answer's yes. And the third reaction isn't so much a question, but it's almost a visceral reaction. People say, oh, I never understand any of that stuff. And I think it comes from the fact that we give the impression, Brian Cox and me and many of us who talk about astronomy, that when I say there are hundreds of billions of galaxies out in the observable universe, I think you think I know what I'm talking about. Or at least I think you think that I in some way can see those things and know what it means to envisage 100 billion galaxies. And in truth, I just get used to saying the number more than most of you. And so it's not that we have a deep understanding, but you can familiarize yourself. You can be at home in this vast universe. We can learn to live in this universe, which you all now know is very, very big, by remembering how we've come to understand it and how we've come to find ourselves existing in this. And you can go a long way just by looking. One of the things I like about astronomy is that it's not a subject necessarily that's about doing clever things. Often it's about making really simple measurements very well and very carefully, and paying careful attention to things that we see around us. So if you look at a completely gratuitous photo of the night sky, we see stars in their multitudes here. We see gas, from which we've come to learn that you can make more stars. And you can see there's this dark patch here, maybe on the left, just here. This is not an area where there are fewer stars, but this is a place where dust, tiny particles, much smaller than sand grains, made of carbon and silicon, where dust is blocking out distant light. And from that dust, and from other similar material, we've learned that you can make planets. And so just in this image, we've got the raw materials for our own neighborhood. But to realize that, of course, we have to realize that the stars are distant from us. That was mostly, although people had talked about the stars as suns and speculated, in the Western tradition at least, of stars being the same as the suns going way back to BC years, really the scientific understanding, the measurement of a distance to a star came only in the 19th century. And that wasn't from want of trying, it was because the stars were much further away than people thought they were going to be, and so the measurement proved to be difficult. One of the things that people have been doing is looking for what astronomers call parallax. So looking for a shift in position as the Earth moves around the sun. If you're looking at a relatively nearby star, it should move from side to side compared to more distant stars. The traditional way to do this is to hold your hand up, line up a finger on something in the distance, and you can flick between your eyes and you see your finger moves. This, should you wish to try it, will allow you to calculate the distance to your finger, which is occasionally useful in life. So that's two things you've learned tonight. The universe is big, and you now have a method for calculating the length of your arm, should you need to. When you try this with stars, right up until the 19th century, they found that very few of them moved at all. In fact, there was no consistent movement, and it took telescopes and careful measurements of tiny fractions of a degree to be able to detect that the nearest stars were at what we'd call a distance of a few the first one that was the parallax was measured was a distance of about 10 light years. And in fact, the nearest star is a few light years away. So for scale, the sun is 8 light minutes away. That's the sort of scale we have been working on. With this measurement, we suddenly have a galaxy, what would have been called, and which gives us the title of tonight's talk, an island universe, a system of stars. They were able to measure parallax to some of them. Of course, many were fainter and assumed to be further. And quickly in the 19th century, we got to the point where we can make spectra of stars. We can take the light from stars, just as people had done with the sun, split it up into its constituent wavelengths, split it up into a rainbow if you prefer, and you can see in these spectra of many, many stars taken very recently, features like these dark lines that correspond to particular elements and which match what we see in the sun. And so we can not only find stars, but we can understand that some are hotter, some are smaller, some are brighter, some are less luminous than our own star. So this is the point where the sun gets reduced to just one of many. And so already 150 years ago, we've got to the point where we're lost in a sea of stars. But they've also become more familiar. And so hopefully that doesn't feel too bad. Now the question comes whether that island universe, whether that system of stars is the only one in existence. And people have been talking about this for a long time as well. In fact, they've been arguing about it scientifically since the first great telescopes were invented, telescopes that were capable of resolving objects in the night sky. And amongst the first to really tackle this question, to understand what the scale of the universe was, were the great observers William and Caroline Herschel, working in Slough and then in Bath. And they're famous because William claims the discovery of Uranus, a planet he wanted to call George, which would have saved all of us a lot of fuss, particularly when talking to primary school audiences. So if you want to call it George, then that's fine by me. He was a brilliant observer, but also a telescope maker. He built the finest instruments around, and that gave him an advantage. He found more lucrative than his previous career, which is as a jobbing musician and composer. There's a wonderful story that he met Haydn and compared notes. This is at the peak of both men's fame. And when I was first asked to think about this, I had a great time talking about what Herschel and Haydn must have discussed. Herschel was writing about star formation and the creation of the universe. Maybe those ideas are echoed musically. And I foolishly said this on a TV program, only to receive letters from historians that pointed out that their diaries exist. And these were essentially two freelance people, and so they talked about how much money each was making. Herschel couldn't believe how much an oratorio was going for, and Haydn couldn't believe how much Herschel was making out of building telescopes. But if you've got the best telescopes in the world, you can do interesting things. And as well as scanning the sky to look for planets, Herschel decided that he could map the extent of what we would call the Milky Way. And so you have to make some assumptions to do this. You have to assume that your telescope is capable of seeing every star in existence. Seems like a grandiose claim, but if you've got the largest telescope, you might as well make that assumption and see where it takes you. You also have to assume that the stars are evenly scattered throughout the galaxy, that there aren't places where there are more stars per cubic light year or something like that. And then all you do is you look at the sky, or in fact, if you're the Herschels, you look carefully at patches of sky on the clearest nights you can through the biggest telescope you can build. And this is a good example of astronomy being about simple measurements. What you do is you count the stars in different directions. They literally counted them in about 600 patches of the sky. And in sieving through those observations, in catching all the faint starlight that they can, in seeing stars and paying attention to them briefly that no one else had ever seen, they're able to work out the rough shape of the Milky Way and produce the first map. So I'm going to show you this map. I think because of that effort, because of what it represents, a first glimpse at a position in the cosmos that isn't just a scatter of stars and isn't just I think this is one of the great images of scientific history. Unfortunately, it looks like roadkill. And you can sort of see why this isn't on T-shirt. Somebody should make this with Gresham merchandise. We'll get this out as a T-shirt if I've got anything to do with it. So this is the map. This is the actual drawing. And it contains one big truth and one lie. And so lie's unfair, one falsehood. The big truth is that we live in a pancake of a galaxy. That there are places on the sky, and we all know this because we see things like the Milky Way with this stripe of stars down the middle. There are places on the sky where when you look, you see a higher density of stars. In the summer and the winter, from here in the northern hemisphere, we look out and we see the stripe of the Milky Way overhead. In autumn and spring skies, from here, we look out of the pancake, up or down on this image, and we see the distant universe and a sprinkling of Milky Way stars. And so that's right, we really do live in a pancake. Now, Herschel didn't know, or at least didn't think hard, or couldn't work out how to overcome the effect of the dust, this material that blocks out the distant light that pervades the galaxy. And so he didn't realize that he wasn't seeing most of the system. And so what that means is that the limit to which he could see was bounded by the dust, not by the edge of the galaxy. And so he got a roughly circular shape with us in the middle. And so this splodge in the middle, the heart of the roadkill, is us. And so he preserved the solar system's place at the center of the galaxy. And we still do this sort of thing. We still do star counts. We can still map the galaxy. We could look at the distribution of gas, particularly with radio telescopes that can see through the dust and allow us to explore the rest of the galaxy. And when we do that, we get modern maps of the galaxy, which look like this. So this is an artist's impression. We haven't yet sent a probe up to take a picture, but it shows a galaxy looking down on a pancake with maybe 2, maybe 4 spiral arms, depending on how grand you like your spiral arms. We live in a spur off one of those arms, about halfway between the center and the edge. There is a bulge, a small one, actually, compared to other galaxies, at the center of the Milky Way. And you might perhaps be pleased to know there's a bar at the center as well, to which the spiral arms attach. And so Herschel had most of this, not all of it, but we knew in the 18th century that there was a shape to the system that we lived in. And pretty quickly, people worked out we weren't in the center. So then the question becomes, are there other island universes? Is this the whole of creation? Is this the whole of the universe? Or are there other pieces to this puzzle? And using telescopes all over the world, astronomers had begun to map the presence in the sky of faint fuzzy things, which clearly weren't stars. So, for example, in the constellation of Orion, here, where you have Orion's belt, this is now rising in the early morning, but will be a familiar sight over the winter months for those of us here in the north. Below the belt, there is Orion's sword, and if you look with the naked eye, you'll see that one of those stars, even from London skies, one of those stars appears slightly fuzzy. And that fuzziness stood out to astronomers. And as they started to scan the sky with telescopes, they realized that there were many such fuzzy things. Some of them were close enough that their nature became clear. Here's a gratuitous modern picture of that fuzzy patch in Orion. This is the lit-up bit of the Great Orion Nebula, which is our nearest star-forming region. It's gas that's lit up and excited by they're actually quite massive stars that have just formed from this gas inside. And it's the light from the newly formed stars that are only a few million years old that lights up the galaxy and casts these beautiful shadows with dust and sculpts the material. This was described by William Herschel, as an unformed fiery mist, the chaotic material of future suns. And there's the essence of that is right. He's able to say this is a place, it's a nursery from which stars are forming. There's also a famous result that looks at the chemistry of the Orion Nebula, which tells us that it smells of raspberries, which Herschel didn't know, but I think would have worked in to his poetic description if he could have done. We continue to look and study the Orion Nebula. This is a result that only came out a few weeks ago. This is a close-up of part of the nebula taken by the JWST, our newest space telescope, built by NASA and the European Space Agency, and sending back beautiful views in the infrared that allow us to peer deep into the heart of the nebula. And what you're seeing here is in detail the effect of the young stars down here on the nebula. So this is an eroding flank at the top. This dusty material is being evaporated by hot ultraviolet radiation from the stars at the bottom. And this image is enough for somebody to spend an entire PhD trying to understand the details of what's going on here. So, though they didn't have these images, our 18th and early 19th century astronomers knew that there were places that seemed to be forming stars in the universe, that some of these fuzzy patches were forming stars. By the middle of the 19th century, they also knew that some of them had distinctly different shapes. And the telescope that cracked this mystery is one of my favorites of all time. It's called the Leviathan of Parsonstown, built by the Earl of Burr in Western Ireland, which continues to be a really strange place to put a telescope, where you need clear nights. But there was an essential realization that Burr had that made this telescope special. He realized two things. One is that the hard bit of building a telescope, when you get big enough, it's all hard, but often the hard bit isn't the mirror, it's the mount. It's how you take what's often quite a heavy mirror and swing it around the sky with great precision. But Burr also realized that if you've got the largest telescope in the world, it doesn't matter where you point it. Interesting stuff is going to happen. So you can improvise with the mount. And so his mount was essentially two large stone walls with a telescope slung between it. And what you do is you wait for an object to turn overhead, and you get about an hour and a half, depending on how high in the sky it is, to observe something, and then you have to wait for the next night. But who cares? You have a larger telescope than anyone else. And what Burr and co. did was demonstrate that some of these nebulae, these fuzzy patches in the sky, well, some of them turn out to be spiral. So here's a drawing which was made of a nearby galaxy. This is the Whirlpool galaxy, M51, from this telescope. And you have to remember that somebody made that sketch while standing on a platform at the top of this structure in the cold of night, leaning over to try and look through. I've used this telescope. It's scary. And I certainly wouldn't like to be standing there and sketching. But they did a brilliant job. And so here is the sketch. So this is 19th century. Here is a recent Hubble image of the same galaxy. And you can see that it's almost bang on. It's a really impressive piece of work. But what this meant was that there were two types of galaxy. Or two types of nebula, sorry, it's so easy to slip. There were the things that seemed to be star-forming, and then there were these spiral nebulae. So are these spiral nebulae galaxies? Are they like our Milky Way, or are they some strange part of the star-forming process? This debate continued into the 20th century, and in fact there was something called the Great Debate, which was held at the Smithsonian Institution in the early part of the 20th century. The arguments on both sides were fierce, and they're kind of interesting. On the everything is a nebula side, the arguments come from what might seem like common sense. So they say things like, but if these are galaxies, we don't see any individual stars in them. So they must be very, very distant, and that's implausible. I mean, that's true. They say things like, we don't see any rotation in there, so how can they be nearby objects? Well, not everything rotates. The cleverest argument, I think, comes from, they'd also been in a nearby spiral nebula, there'd been a bright nova, what we would call a supernova. And again, the everything is a nebula crowd said, look, a new star appeared in that object. It outshines the rest of the galaxy, the rest of the object. I should have rehearsed more. The rest of the object. I've ruined the punchline. You now all know galaxies exist. Good job I gave it away at the beginning. This new star on its own outshines the entire galaxy. Well, that's clearly ridiculous. It can't be made of stars. It must be a gaseous thing, and this is a new star that's made. And again, that's sensible, except that we now know that supernovae are briefly, because of the decay of the radioactive elements that are produced in the supernova, they are capable of outshining an entire galaxy. And so, on the other side, there was I think the cleverest argument was somebody who pointed out that new novae, these new explosions that we see, sometimes from the death of massive stars, but sometimes things like binaries that interact violently, they pointed out there were more of them seen in these spiral nebulae than elsewhere in the galaxy. So if they were part of our galaxy, why did they preferentially show this violent phenomenon? And the debate remained unresolved until we could actually measure the distance to galaxies. To do that, in the 20th century, people started using particular kinds of star. And the most famous of them is a famous star in its own right. It is our current pole star, Polaris, which you find in the north from the familiar asterism of the Plough or the Big Dipper, depending on which side of the Atlantic you're on. You follow the pointers on the right-hand side of the saucepan up to Polaris in Ursa Minor. It's not a particularly bright star, but it is near the celestial pole, and so it appears that all the stars turn around it. It's useful for navigators and so on. But I think slightly ironically, given that there have been poems written and hymns sung to the constant navigator's friend Polaris, it's a variable star. It changes brightness over time. I've got a video of it here. And you can see that over the course of a few days, in fact, this is sped up, the star seems to flicker. For those who prefer data to video, here is a light curve that shows that change in variation. It's very small, it's quite subtle, but it's changing regularly, it's pulsing, and so its brightness is changing. It is in fact a kind of star called a Cepheid, and these Cepheids have an almost magical property. They change brightness because they pulse, but how fast they pulse depends on their luminosity, how much light they're putting out into the universe. And so if you can measure how fast they're pulsing, then you can work out how bright they should appear in the sky at different distances. And so then you can compare how bright they do appear to how much light you know they're giving out, you get a distance. And they're bright enough to be detected with large telescopes, mostly in the US in the first half of the 20th century, in distant galaxies. And this is the measurement, though it took 20 to 30 years to calibrate it, that tells us definitively that we live in a universe of galaxies. That the Milky Way is one of a whole collection of island universes of distant galaxies. And enables us to do what lots of my friends spend lots of time doing, like go and study distant systems and try and understand them. This is a beautiful irregular galaxy, NGC 9061, a spiral disrupted by material falling onto the black hole at the center, imaged here by a team led by Julian Delcanton. The galaxy's on the left, Julian's on the right, just to be clear. But we can also, though it's tempting to linger and tell you about my 250 or so favorite galaxies in detail. Could do that another day, perhaps. Maybe I'm going to run out of ideas in a couple of years' time. But the other thing you can do is take these galaxies and think on a grander scale yet. Because now we've gone from the sun to stars to the Milky Way to galaxies, you can ask whether there's a bigger structure still. Whether on larger scales the universe is structured. And so what you do is just as we plotted the Milky Way by plotting the positions of stars, you can take these beautiful galaxies and reduce them to a point each, and then you can make a map of the distribution of galaxies in the universe. And this was first done in the late 1980s, and this is the first large-scale map of the universe, so another iconic image in astronomy. The map has us in the bottom, and we're looking at a patch of sky, so you get this wedge shape. And each dot here is a galaxy. You can see a couple of things. One is that there is structure here. There are places where there are lots of galaxies, and there are places where there are very few galaxies. And please ignore the fact that it looks like a stick man waving arms. I promise that's a coincidence. You can imagine the reaction to the fact that the universe looks like a stick man waving long arms. Actually, it looks like those things that you have on top of car sales rooms that flail their arms around. So maybe there's a cosmic message there. Who can say? What we have done is done this on a much grander scale. There was a telescope called the Sloan Digital Sky Survey that for 8 years did this extraordinary thing of sitting on a mountaintop in New Mexico and allowing the stars to turn over it, allowing the sky to turn over it, and using its camera to record whatever floated through its field of view. On the clearest nights, it went back and measured the position, the distance of about 1 million galaxies. And so it allowed us to create a three-dimensional map of our neighborhood. So this is real data that you're seeing now. This does look like the opening of a low-budget sci-fi movie, but these are galaxies in their correct positions. And you can see the lumpiness of the cosmic web, which I described, the places where there are lots of galaxies, places where there are very few. On the left of your screen right now is a C-shaped structure called the Sloan Great Wall, which is so large that we think it ought not to exist in our universe. And actually, recent results seem to show it doesn't, that there's actually 3 separate things. But still, there are 200,000 galaxies aligned in what appears to be a great wall. In a minute, with no expense spared, I will stop and rotate the universe for you, and you'll really see this honeycomb structure. What I want you to do, though, is ignore the fact that it looks like a bow tie, that there are gaps in between. Those gaps are just the places in the universe where we haven't filled in the details yet. So you can think of that as "Here be dragons" on a medieval map, written on the largest possible scale. They're actually mostly places where our Milky Way, that pancake, gets in the way of viewing these distant galaxies. Now, I think this data is beautiful. And you already know that I love each individual galaxy, even the fuzzy ones further out. But there's a slight tendency from scientists to try and reduce beautiful data to simple measurements. We've already seen you can take the galaxies and turn them into points on a map. And we've restored them a bit in this animation. I'm a big fan of some work that was done by Carl Glazebrook and co. around the time that this survey was released, where they asked the simple question, which is, what is the color of the universe? So they said, okay, we've got 1 million galaxies. What happens if I take all the light from those galaxies and work out sort of what the average color of the universe looks like? Sort of for fun, but it also tells you a bit about the history of the universe. It tells you a bit about star formation. When stars form, big blue stars don't hang around for very long. So if the color of the universe is bright blue, we know it's a vigorous, healthy universe with lots of star formation. If it was just faint, dead red stars, they last for a long while, but we know that the universe wasn't forming stars. So they did this, and they put out a press release and said, this is the color of the universe. A color that's very familiar to people who've seen the Gresham logo. So this is very satisfying. However, shortly after they put this paper out, they were contacted by an expert on how the eye perceives color, who pointed out that the program they'd used didn't work the way they thought it did. So while the input data was right, this is not the color of the universe. So they had to put out a second press release, which transformed the color of the universe into this, which they tried to save by naming this color Cosmic Latte, a name which, and I checked, has been used precisely no times in the scientific literature since. But it means we live in a sort of universe that's neither too hot in the sense of star forming, nor is it too quiet. We live in a universe that has all sorts of galaxies within it. But I still find that kind of satisfying. There's a serious point here as well, because by making this, it's almost a ridiculous measurement. Take all the light that you can collect from the universe and reduce it to a single color. But in doing so, you've also reduced it to a single measurement of brightness. It's as if I've taken a light meter out into deep space and just said, okay, what's the background light? If you think about it, that's going to tell you how many stars and galaxies there really are in the universe. And what's amazing is that we've just done this experiment. We did this experiment with a probe that was designed for something else. It's a probe I'm sure lots of you have heard of because it went here. This, of course, is the image of Pluto from the New Horizons probe, which visited it 8 or so years ago now. Now, Pluto's not a planet, and we can fight about that later. That should fill up the questions nicely, I think. But solar systems next time, anyway. But it is a fascinating world, and New Horizons showed us that it was a place of much interest with mountains made of water ice and this heart-shaped smooth area called Sputnik Planeta. But, unfortunately, mainly for cost reasons, much easier to do a flyby than to go into orbit around a world in the outer solar system. So New Horizons shot past, and we've already got all the data we'll ever get on Pluto from this probe. It visited a small Kuiper Belt object, another denizen of the outer solar system, but it's now speeding out into interstellar space. There it is, just to give credit where credit's due. But its instruments are still working, and one of the things it's doing is doing exactly this measurement of just measuring the background light. And from New Horizons, the result is that there are at least 200 billion galaxies in the universe. And we know that because a probe that we sent into the outer solar system is detecting light from all of them. Not much of it, admittedly, but I still think that's rather fun. We may be missing, it may be even grander than that. Remember, space is big. Others who've thought about contribution that you get from galaxies in the infrared light that's been stretched by the expansion of the universe, more on which soon. If you add those in, there may be 2 trillion galaxies in the universe. And hopefully, as we've got there step by step, that doesn't feel quite as scary as it might have done when I started. Though I admit, I realise that I haven't actually defined a galaxy at this point. And I've done that deliberately because the definitions got rather fuzzy recently. Remember, we started with an island universe, with the Milky Way in grand splendour alone in the universe. And then we got other island universes so impossibly far away that even astronomers didn't think they could possibly exist. But we now know that a galaxy's life is full of social events, of interaction with, admittedly often violent interaction with neighbours. And we know that partly from studying our own galaxy. There is an incredible satellite called Gaia, launched by the European Space Agency. Europe in space specialises in a few things. We like comets, we're good at that, and we're good at mapping the sky. It's always been a speciality. And Gaia has mapped, most recently, the nearest 1.8 billion stars. So 1 or 2% of the population of the Milky Way. And this is a map, actually almost You could literally call this a photograph of the night sky with the dust of our Milky Way running through the middle and our twin neighbor galaxies, the large and small Magellanic Clouds in the bottom right there, from that Gaia data. It's a small telescope, but it works with exquisite precision, measuring the distance to these stars with such accuracy that the spacecraft designers and the astronomers who use the data have to worry about which side of the spacecraft moonlight is falling on, because that's enough to affect the measurements. And if that's not impressive enough, Gaia doesn't orbit the Earth, it's 1 million miles away. And so you still have to worry about where the moon is. But Gaia measures not just position, it measures velocity. So we understand how these stars are moving. And so we can do fun things. For example, I've now highlighted the 40,000 nearest stars to us, and I can run their motions 1.6 million years into the future. And basically, it's a mess. But what you realize is that our galaxy is a dynamic place, that stars are not just orbiting sedately within the pancake. They're moving in and out, they're interacting with each other, and they're surfing, literally, the galactic tides. Now, if you start to look in detail at these patterns, you find there are clusters of stars that move together. Some of them may have been born together, for example, if they're young. And for example, if you think about the Plough, 5 of the stars of the Plough, plus a few stars all over the sky, move together through the galaxy. They most likely formed recently and have yet to disperse in the wider population. I guess it's like a bunch of kids going to the same university from the same school or something like that. They will soon scatter. That analogy doesn't work. Never mind. Keep going. Stop improvising. Sometimes, though, you see grander moves. And some of the streams of stars that we've seen moving through the galaxy are the result of collisions with other smaller galaxies that took place billions of years ago. The most significant of these seems to have taken place something like 8 or 9 billion years ago. And it was the major event in the history of the Milky Way. We hit a dwarf galaxy that was perhaps 20% of our own size, or rather, it hit us, and its stars were absorbed, but yet their motions still carry the signature of this ancient event within the disk of the galaxy. I'm delighted to tell you that this most important event has been given a name by astronomers. In fact, we've named the dwarf galaxy that we hit. We call it, with due solemnity, the Gaia Enceladus sausage. Astronomers should not be allowed to name anything, but we can simulate what happened. This is a lovely simulation of a similar event from a large cosmological simulation. You can see that the little galaxy comes in, hits the proto-Milky Way, and they dance together. We may even have found what I'm afraid I have to dub the core of the sausage, in the form of this cluster, NGC 2808, which has been known for a long while, but moves along with this stream of stars. And so this may be the dense remnant of the core of this ancient galaxy. A collision that happened a little while later than that, with a galaxy that we still see in the sky today, the Sagittarius dwarf galaxy, may have had more profound consequences. It had an encounter with the disk of the Milky Way about 6 billion years ago, before coming round as a stream that we see in the Gaia day today with a dense core that we still spot. If you look in the summer sky towards Sagittarius, you're picking out a few stars from this interloper, and we see these long tidal tails around the sky. But that peak that happens about 5 or 6 billion years ago corresponds to the time that the sun itself was forming. And collisions of galaxies like this, while there's enough space in space, which is really big, such that the stars don't collide, the gas in the galaxies does get disturbed and mix up, and these mergers trigger an ostentatious display of star formation, a firework display. And so it's possible that our sun's existence owes its history, the fact that the sun is here, and it's the star it is, and that it formed when it did, to this history of collisions. And grander things are coming. We know from projecting forwards that the Milky Way galaxy, our island universe, will soon collide with a more distant system, the Andromeda galaxy, our nearest big galaxy, currently 2.2 million light years away. We have 3 galaxies in our local neighborhood, 3 big ones. The Triangulum galaxy in the top left is a spectator. But in about 4.5 billion years' time, shown in this simulation, these 2 galaxies will interact. And again, while every star should remain unscathed. There's no danger to the Earth around the sun. You'll all be able to enjoy this over the course of a couple of billion years. I assume we'll all be uploaded to something by then. You get these long tidal days and bursts of star formation before you settle down into a new large galaxy, which we've decided to call Milkdromeda. Astronomers should not name things. We've got 4 or 5 billion years to come up with a better name. This kind of interaction is common. If I zoom out in a simulation, then what you see, and this is a few billion years of cosmic history on a grand scale playing out for you, what you see is that these island universes are nothing of the sort, that they collide and merge and form large structures. We live in a connected universe in which the properties of the galaxy we call home are dictated by the environment in which we find ourselves. This is a story we can confirm by using another astronomer's trick. I'm always envious of scientists who get to study the objects of their research in the lab. It'd be much easier to reach out and turn the Andromeda Galaxy over and have a proper look at it instead of being stuck with it nearly edge-on, inconveniently millions of light years away. But if we stare into the deep sky, we can time travel, though only to the past. But we get to watch the early stages of bits of our universe because the light from distant galaxies takes so long to reach us. So this was first done in earnest back in the mid-90s when a familiar patch of sky, there's the Plough or Big Dipper, a patch of sky that's about here, a patch of sky that is about 1/24 millionth of the entire thing. That's a pinhead held at arm's length, roughly, was selected by a team at the Space Telescope Science Institute to look for the Hubble Space Telescope to be pointed at this patch of sky for over 100 hours. And it was partly done for scientific reasons, but it was partly done because the staff needed a break over Christmas. So they wanted to do the simplest possible observation, which is looking at the same patch of sky again and again and again and again and again and again for about 10 days. They picked the most boring patch of sky imaginable. There are no bright stars, there are no known galaxies there. And many serious astronomers, when I started looking into this, it was a surprise to me that many serious astronomers who'd made their life's work studying galaxies thought that this observation was pointless. They argued that there was no chance that Hubble would discover any new galaxies. But when this image was released just a few weeks after it was taken, it showed a sky speckled with distant galaxies. Almost everything in this image, the Hubble Deep Field, is a distant galaxy. Many of them with so far away that their light has been traveling towards us for billions, in fact, more than 10 billion years in the case of many of the faint, fuzzy objects in this image. So why did the eminent astronomers get it wrong? Well, they made the mistake of assuming, it's the same mistake we keep making, we made the mistake that the distant universe would be like the universe around us. We've made this mistake on almost every scale imaginable. They thought that galaxies would be like the Milky Way. And they're not. In this early universe, they're smaller. But they're also more active. They're forming stars at a rate that would be incredibly unusual today. This is the universe's first great flourishing, what people now sometimes call cosmic dawn, a period in which star formation ran riot. And so these galaxies shine brightly, and we see them from all of this distance. And this game of staring into the distant universe for a spot of time travel is now almost the first thing you do with any telescope. When the JWST, with its golden mirror, sensitive to infrared light, was launched on Christmas Day 2021, almost the first thing, once the telescope had unfolded its sun shield, commissioned its optics and set to work, was to start staring at the distant universe. One of the first images that came out 6 months later was this one. There's a lot going on here. This is an image primarily of a nearby cluster of galaxies, the orange-yellow things you see at the center. But they're being imaged because they act as a natural telescope. Their gravity bends light from the galaxies that are further away. And so you have these long red arcs, which are actually very distant galaxies. The images are distorted. This isn't a very good telescope mirror, but it is powerful. And you can see there's one up here. There's a little red stretched thing near a yellow galaxy, which sort of really exemplifies what can happen to these distant images. In the literature, we talk about these things being sluggified, which is a technical term. But the real excitement of this image when it first came out isn't all of this show in the middle. It's the few tiny red dots you can see around the edge. Because JWST is a big enough telescope with a 6-point-something meter mirror, and it's sensitive to infrared light, which picks up the galaxies from the very early cosmos. So these faint red dots are galaxies, and this is a close-up in my tradition of showing you excellent images. This is a close-up of a galaxy whose light has been traveling towards us since the first billion years that the universe has been in existence. And we've found loads of these things. The one on the left here is seen 350 million years after the Big Bang. The one on the right seen 450 million years after the Big Bang. And what we're beginning to realize is that the universe started not just with a bang, but with a show. That star formation and galaxy formation got going quickly. That galaxies have been part of our story since the first billion years. We can confirm these in other ways as well. As I gently mocked Carl Glazebrook and his colours of the universe, I should say that a team that he leads have been studying this thing. And people who study these kind of galaxies are known affectionately as blobologists, by the way. So I understand this isn't a beautiful spiral, but this is a galaxy called ZF UDS 7329. I know many of you will be familiar with it. This is a galaxy that we see 2 billion years after the Big Bang, but it's already filled with old stars. So we can tell from its light that it contains the remnants of this initial burst of star formation. So wherever we look with this brand new telescope of ours, we're beginning to see evidence that the universe was born young. Of course it was born young, but it was active and filled with young stars. And big surveys like this one, these are the results from SEERS, survey using JWST. Each image here represents only an hour of time on the telescope. But together, these images, which show the merging of young galaxies and this firework display of bright stars, show 100,000 galaxies, 11 of which we're already sure existed when the universe was only 500 million years old, and lots of which look mature. They have large black holes. They have young stellar populations. And though we realized long ago that the universe was very big, we're beginning to realize that we didn't really understand the richness of the story that it had to tell us. And in fact, the presence of these galaxies, though there's much work still to do in the years ahead, which I will hope to tell you about as this course of lecture unfolds, we're beginning to realize that we don't understand something. That our descriptions of how the universe should have formed and evolved, the descriptions that feed into the simulations that I've showed you, may be missing something. And the early universe may have surprises for us that we're only now beginning to unfold. So when you look up at the night sky, you should feel, I think, that you are a member of a vast cosmos, that you are on an ordinary planet, around an ordinary star, in an ordinary galaxy that has a long history involving something called the Gaia Enceladus sausage in it. But hopefully, the fact that we are able to look up at the sky, to build instruments capable of telling those stories, and that there's still new stuff to find out, will inspire you as much as it inspires me. Thank you very much for coming. I'm delighted to be here.
This one is actually really an important question for those of us who are trying to get a handle on how big the universe is. Right? It's saying, will it ever be possible for humans to have a comprehension of scale? And not just in terms of a mental one, but a theoretical one. How do you spot the beginning and the edges?
Yeah, it's a really good question. So I want to be really clear that I don't think this stuff is ever going to become common sense for anyone, including me, right? It's weird that we live in a big universe because we're built to live on a planet. And we evolved, and our brains evolved to live on a planet. So it's fine to find it odd that we live in this entire universe. Though I think this does drive sometimes people to send me theories because they think the universe should be simpler than it is, and they found the answer. And you can, We can talk about that later. I think theoretically, is there ever an edge? We've got a really good idea. There are good reasons to believe that the fraction that we can see is only a tiny, tiny, tiny fraction of the whole. So even though we've got this vast observable universe, I think most physicists would bet that we're only looking at a tiny, tiny fraction, in which case we'll never see an edge. What there is, as you know from previous lectures here, is that there's an end, right? That we live at a time in which there's still star formation in galaxies and all this joyous stuff to enjoy. That won't last forever. So I think, it's not so much about us spotting an edge, it's us enjoying the universe that we've got for at least the next 20 billion years or so while we've got it.
Okay. So we're going to the Gaia sausage now, which is clearly important. Does it have a central black hole?
This is a great question. So they said that this cluster may be the center of, might be the center of the sausage. And it's true that most galaxies, even small galaxies, dwarf galaxies, have black holes at their center. So this would predict that that cluster has a black hole at the center. The trouble is that globular clusters like this are so dense with stars that it's very difficult to see. In fact, it's impossible to see the center. So we don't yet have a way of testing that idea. But in theory, sure.
So I'm rather attracted to this one since we came across raspberry-flavoured galaxies a little.
I should say you'd need to scoop up an awful lot of the Orion Nebula to smell anything. So let's make that clear.
So what was it called? The Milky One. I came across its name.
This is in the Orion Nebula.
Yeah.
Milkdromeda. Yeah, so Milkdromeda was the combined Milky Way plus Andromeda.
What flavour is that one?
Well, we're open for sponsorship, I think. That's probably the clearest answer.
Rather good, yeah. Okay, so how do you differentiate between the brightness of galaxies and, say, quasars or other bright objects? What is it that distinguishes them?
Yeah, so when I said that the Sloan survey scanned the whole sky, capturing pictures of everything that crossed its path, that includes asteroids, it includes satellites, which we have to get rid of because they streak, but it includes, as you hint, quasars, which are distant objects with bright emission from material that's falling into their black holes. So how do you know that things are a galaxy? Well, there are two ways. One is that you look for fuzzy patches. So it's the same measurement that they were arguing about in the late 19th century. If it's fuzzy, it's probably got an extended disk, and so you bet on fuzzy things, and then you go and take spectra and confirm them. In the same way, JWST images, people are looking for small red dots, and then taking spectra to confirm their distance. But the other thing you can do is that galaxies often come in particular colors. So you can distinguish some types of object by looking at what color they are, and that gives you a good sense of what you're looking at. You can do that very carefully with many different filters, and that helps too.
You showed the picture of William Herschel with Caroline.
Yeah.
I think you talked about William, but what role did Caroline play?
So they did. So it's interesting, and I'm not a historian, so there are excellent scholarly works on this that I point you to. So they observed together, and she was a superb observer at the telescope, and they would both record both of their observations. So for that work, she was the first woman to win the gold medal of the Royal Astronomical Society, for example. She won at a time when most women weren't allowed in the Royal Astronomical Society. The writing up of the work was in William's name, and I think, so when I talked about his description of the Orion Nebula, I think that is his, but as an observational astronomer, she was reckoned to be the better of the two. And so it was a true partnership between the two. Thank you for asking.
My question about the early development of galaxies grew quicker than astronomers can account for. Do you think that observation is a mystery on a par with dark matter and dark energy, pointing to new physics?
Yeah, so I think that it's a great question, and it's something I will return to later in the series. So could it be new physics? I think we don't yet know whether it's new astrophysics or new physics. So one possibility is we could change how perhaps gravity works in the early universe so that you get a lumpier universe more quickly. That would help. But it may just be that we don't understand. This is a very alien environment from us. The background temperature is higher in the universe. These galaxies have come together quickly. We don't know what roles black holes that form in these galaxies will play, but perhaps that might be a stimulus to star formation. We also know that the first we think we know that the first generation of stars will have been very different. So the very first generation of stars will have been very massive, and they would have lasted only a few million years before exploding, and they will have had an influence on the galaxy. So it's possible there's an astrophysical story here. I think people will think about that first, and then we'll talk about the physics. What we're doing at the minute, wonderfully, is counting the things, because it's really important to establish how many there are, when they appear, and for that we need more telescope time, and JWST is very busy doing this.
My question was going to be following on from that in a way. It's clearly a spectacular tool, having that thing floating around, taking pictures of what you want it to take picture of. But who is managing the choices that you make to do which studies?
Yeah. So the truth is that if you built 10 of them, it would keep the world's astronomers busy. And so there is huge competition to use this. It's an open competition. Anyone in the world can bid for time on JWST. And what you do is you write cases. Many of my colleagues spend a large part of their year writing a pitch that says, I want to use the telescope for this. And in fact, things like the Hubble Deep Field will have gone through the same process. And that image that revealed all those galaxies, that was rejected several times because it was a risk. These proposals are often interesting. You have to say that your use of the telescope will transform science, but you have to know exactly what the result's going to be. And so this is sometimes difficult, but it's essentially a bum fight, but it's a bum fight adjudicated by scientists. So we're judged by our peers who hand out this time.
Who are they? I mean, how do you get to be a chooser?
So it's viewed as service from the community. So people who've used the telescope, who have expertise. There is one of them in this room, but I'm not going to tell you who it is. So they're drawn from the community of people the sort of black belt users of the telescope are the people you're looking for. Also people who agree with you. That's always helpful.
Got the same grant. Okay, we'll just do one more question, and it's to wind up with. What's the worst name you've ever chosen for anything in astronomy?
There are some really, really bad ones out there. I'm going to go for... The prize goes to the people who discover planets, because you get catalogue numbers. And so my favourite... I've got a whole lecture coming up on a star called KIC 8462852, and that's a pretty good one. And there are planets called things like Ogle 4743589b. And I think, if there are aliens out there, they're going to have a word when they discover what we've called their planets.
Thank you. Ladies and gentlemen, please thank Chris Lintott for his first lecture and look forward to the rest.